All right. So again, thank you for waiting, and let's get on. Hopefully, gave you all enough time to get some coffee and wake up. Anyway, I had to jump a fence, but so we have different activities, right? So today we are going to look at the last part of the Bode plot lectures. Last week we spent some time and we saw how to do the asymptotic Bode plots. Remember, what we're trying to do is to find a shortcut way of doing frequency responses. And we were able to do that by approximating the frequency response by straight lines using certain behaviors that we identified, right? So we saw, first off, you start with the transfer function, and then you substitute the S equal to j omega in it, and then you grouped it in a particular way, 1 plus the j omega over the break frequencies. And by doing it that way, it made the low frequency lines 0 dB all the way across. So we were able to sort of standardize how we drew the frequency responses. And basically what you do is that you break the transfer function up into its fractions. You factorize the numerator and denominator. All the numerator functions would be zeros, and all the denominator factors would be poles. And once you put it in the standard form, because we are expressing it in decibels, which is a log, all of the multiplications and divisions become additions and subtractions. So you simply put draw each set of lines together, and then you add it up at the end. So we did all of that, and we eventually ended up last week where we did a full sort of transfer function with both numerator and denominator, both poles and zeros, and we were able to plot it out. The one thing left, the one sort of unusual creature still left, has to do with the second order responses. And there are second order systems where the poles are complex, right? Remember when we were doing the step responses of systems, we saw that with systems where the poles were complex, you started to get this sort of behavior, right? That when you put a step response on the system, this is in the time domain, when you put a step response on the system, instead of doing this, which is what you normally would expect, or something like this, which is a first order sort of response, that the second order systems had a tendency to oscillate, right? And what made it oscillate was this particular factor, zeta, the damping factor. And the damping factor made the roots of this is a second order system, depending on the damping factor, which was in this range, the roots of this became complex. And at some point in time, if the damping factor was 0, the system oscillated, right? Some systems you do not want that, we mentioned that, but there are other systems, like in the case of electronics, where you're making an oscillator, that you actually want that type of behavior. But in very many situations, what you want is to limit this oscillating behavior, which is why you have to adjust the damping factor accordingly. That behavior also creates a little issue with the frequency response. Remember this step response here, right, was time. This is the time response. So what we're looking now is to see what is the frequency response, omega or F, in the same sort of scenario. All right. Again, feel free to stop me at any time if you need to clarify any matters, or if something you want me to repeat anything. Okay. So the first step, of course, if you're given the transfer function HS, is to make the substitution S, to substitute S with j omega to convert it into the frequency domain. So the straight substitution here, of course, is that you have a j omega squared here, which is going to give me a minus omega squared. You substitute S j omega here. So you're going to have j omega and an omega naught. And of course, this one is unaffected. All right. So the next step, of course, is to rearrange it, to try and rearrange it a bit, and let's see what we do now. Right now we have, if we rearrange it and put the real parts together, so this is a plus j b now in complex numbers, we take the first off, we divide through by omega squared, omega 0 squared. And then we group the real parts together and then the complex parts together. So we get it in this sort of form here. All right, so if I give you a complex number like a over, a capital A over a small a plus j beta, and I ask you the magnitude of this, of course, and I should really put a magnitude sign here, is really 1 over the square root of the real part plus the imaginary part. All right, so nothing too unusual here. I've just taken the original transfer function. We know this from lecture 12, 13, somewhere around there. Right, this was a standard form for the second order equation, which, by the way, most people got correct. I had that question in the midterm. I'm glad to see that most people got that particular question correct. We take that, we substitute S for j omega. So you put it inside of here. Remember, there are 2 omegas inside of here now, right? And then we simply divide through by the omega naught squared on top, and then we group the real and imaginary parts. The magnitude, complex number, so we get the form for the complex number part. So let's look at the behaviors that we're trying to ascertain in the same sort of way that we did before. When omega is much less than 0, okay, when omega is much less than 0, we have, oh, sorry, not much less than 0. When omega gets to closer to 0, or omega over omega naught is much less than 1, all right, then this basically drops off and this basically drops off. So if you look at the low frequency response, as you get closer to 0 here, omega going towards 0, this basically becomes 20 log of A. That's the response. So the response would be 20 log A. All right, let me erase a bit of this. Right, so as we get to the low frequency side, the response is just 20 log A. Right? When omega gets very large, right, well, we have 20 log A remains. Then we have, remember, this factor here is really omega over omega naught to the power 4. Because of the squared here, there's going to have a omega over omega naught to the power 4. So as omega gets large, this factor here will become quickly larger than this factor. So the dominant relationship in this, as omega gets very large, is going to be, well, the 20 log A on the top, which is independent of omega, and the minus 20 log omega over omega naught squared below. Make sense? That makes some sort of sense?
Sir, could you go over that again?
Okay. When, let me just get rid of some of this. You're okay with the first part?
Yes, sir.
Good. Right, so let me get a different color here. Good. So when the other part now, when omega starts to get large, as the omega starts to get large, first off, as omega, this is going up, right? So we have here, as omega starts to get very big, omega over omega naught, first off, is going to get bigger than 1. So in comparison to 1, as omega starts to get large, right, you could ignore that, right? Okay with that?
Yes, sir.
Right. Underneath the square root sign now, therefore, we're going to have omega over omega naught to the power 4 plus 2j zeta omega over omega naught. Well, this is all squared. As omega gets bigger, the omega to the power 4 is going to increase considerably faster than omega squared. So again, as omega gets larger and larger, this bit now, you could start to ignore as we get bigger and bigger, higher and higher in frequency. So what we left with now is A over the square root of omega 4 over omega naught to the power 4, right? Which is A over omega over omega naught all squared, yeah?
Yes, sir.
Right, and we take logs to convert that to dB. So it's going to be 20 log A, which is this bit here, minus 20 log of this bit, which is 20 log omega over omega naught squared. Yeah?
Understood, sir.
Right, and this bit now, we know this, this is minus 40 log omega over omega naught. So in other words, this bit now, as omega gets very large, we still have this 20 log A bit that we had from the first part, but the second part now is going to decrease at minus 40 dB per decade. So as omega gets large, this bit now is decreasing at minus 40 dB per decade. So normally what we would do in our approach that we've taken so far to complete the asymptotes, I simply, let me get back. I simply connect these two lines, and this is what the response, what we would normally assume the response would be. Right? And this, of course, is the corner frequency omega naught. But unfortunately, we have this zeta inside of here. This is going to affect this point considerably. And this is what we're going to try and figure out now. But everybody understand, we got the low frequency line, we get the high frequency line here, but we're going to have to figure out what's happening inside of here. All right?
Yes, sir.
Right, so let's see, well, this is what we have so far. We have to figure out this bit here. Good. So if I give you a function like what I have here, and you could always put back the magnitude sign, the magnitude of h j omega is equal to that function there. If I were to ask you, when is that a maximum? This is a maximum, h j omega is a maximum when this is a minimum. Right, so when the denominator is a minimum, the whole function becomes a maximum. So we don't have to worry about anything. Let's just look at this bit inside of here, right? So I'm going to call that capital D over omega is this bit inside of here. So in other words, I'm saying let h j omega equal, right? That's all I've done right now. And when this is a minimum, this whole thing becomes a maximum. And if you remember from your add maths, right, early on, if I gave you any sort of function and ask you, when is that function, well, a maximum or a minimum? What the first step you did was to take dx dt and see when it became 0. You remember that? Cast your mind back 10 years. So we're going to do the same thing here. If I want to find out when this is a minimum, so I need to find d omega, differentiate that, right, with respect to omega, and then find out when this is equal to 0. When that is equal to 0, then I have my minimum point. Fair enough? Rings a bell? Right? Remember that the function is like, this is you're basically finding a point of inflection here. So when you look at the functions, wherever the gradient of the function is 0, is either a maximum or a minimum, right? So in our case, we take the derivative here. We take the derivative of d omega, which is the denominator, and we set that to 0 now, and we solve for omega. So if you take this here, set that to 0, and you solve for omega. In other words, what value of omega is going to make that 0, you will see that omega is equal to omega 0 by this function here, 1 plus 2 zeta squared. All right? Notice again, when you solve here, so that value of omega is going to make this 0, which means that d of omega is a minimum. And if d of omega is a minimum, then h of omega is a maximum. So at that particular frequency here, at some frequency omega 0 into 1 minus 2 zeta squared, the response, the frequency response, this is this, and we call this omega r, but you'll see in a second what that is. This response goes up to some maximum, right? H j omega max. We'll see what the value is in a second. So we had, before this value, we had 20 log A. After here, we have minus 40 dB per decade. But right where these two lines meet, there is going to be a maximum in the response. Hj omega is going to do some kind of thing like that, right? Depending on the value of that frequency. And that depends on the value of zeta. Everybody following? Is everybody following? Let me make some sense.
Yes, sir.
Right, at least one person. Good, good. 1 out of 87. Anyway, notice a little extra constraint we have there. For this to be, the frequency has to be a real value. So the only way that this square root, right, can be a valid real number is if zeta is in this range, which is not zeta 0.7071, I think it is, right? So before we saw, when we now started out, for the second order system, that the step response had a range of zeta that without oscillating between 0 and 1. But in fact, this value is actually even better, a little bit less. When we do a further estimate here, we see that in fact, it is actually constrained to between 0 and 0.707, right? They call this particular frequency the resonant frequency, right? It is only valid for this range of zeta. But if you know, because of the range of zeta, this usually makes omega r fairly close to omega 0, right? So in many instances, the same value is used. If you try to draw this on a log scale, right, omega r is a little bit less than omega 0. So omega 0 is somewhere maybe here, right? Maybe somewhere right around here. This is really where omega 0 is. But on a log scale, remember this is log omega, it's next to impossible to see that sort of difference. So if one is 100 hertz and one is 110 hertz, you're not going to see that very clearly on a log scale unless you zoom. So because again, we deal with sort of straight line approximations to the behavior, we just want an idea of what the thing is doing. We generally assume that omega r is approximately equal to omega 0, okay? But you could calculate the real value from this to see just how different it is. The next part, so that's telling us that the h of j omega is a maximum. What is a maximum? Well, take this value of omega now and plug it back into this. So you put the value of omega that we just calculated, you put omega r back in here now, and if you do that, you get that the actual value of the response is A over 2 zeta into 1 minus zeta squared. Both of these things you need to remember. Okay, and you have enough problem sets on past paper questions. We'll do it for you to commit that to memory. So commit, you put a little red star here. For your purposes, you need to commit this to memory. And if you remember how to derive it, then it's a lot easier. So you commit this to memory and you commit this to memory. Of course, on the Bode plot, what is displayed is 20 log of this. This is the absolute value. This is the real value on top here. So you need to commit those two things to memory. Let's see what it actually looks like. If I were to plot the magnitude plot, this is what the Bode plot actually looks like for our second order system with complex poles. Right? In my case, A was 1. Right, so this would be a plot of instead of it would be just omega naught squared over s squared plus 2 zeta omega naught plus omega naught squared. Right, I've made the gain here 1. So 20 log of A is at the 0 dB line. As you go past the resonant frequency here, if you look at the graph, you'll see that this is, because it's a second order system, minus 40 dB per decade. And look at what happens at resonance here. This is the damping factor here in this little table. When the damping factor is very close to 0, like 0.01, notice that you have a very high peak in the response. It's going from low frequency is 0. It is going up here to something. This is 30 here, so that is going up to something like about 35 dB, right? So it's 35 dB peaking, and then it's coming back down. At 0.1, that's a blue line here, right? It went up by about 10. At 0.3, it has a little peak of about 5 dB. And 0.7, remember, it's only valid if zeta is between 0 and 0.7. Notice the response. The response is almost like a normal second order system with real poles on it. Everybody seeing that? Making sense? Yeah? All right, so as omega, so the curves, you're going to have to, what if I were to give you a second order system, and there's an example at the end of the slides that you'll do for homework, depending on the value of zeta, you know what the low frequency asymptote looks like, you know what the high frequency asymptote looks like, right? The problem is that you need to figure out what is going to happen at the resonant frequency, all right? What about, this is only half the answer. We need a phase. Remember, the Bode plot has both magnitude and phase. If you go back to what we had before, the magnitude, all right, let me just, right. So this is what we have here. This is what we have. The magnitude, or the argument for this, is going to be the inverse tan of the imaginary part over the real part. Okay, so we put that back here. That is a normal complex number stuff. So the inverse tan, negative because it's 1 over the imaginary part over the real part. At omega equal to 0, we could see that this is the argument is 0. At omega equal to omega naught, this becomes minus 90. And then if you keep incrementing, it will continue through minus 90. And then as omega becomes very large again, it basically, this comes back down. It continues through 90 and it keeps going until it reaches 180. Remember the tan curve is this funny, has these funny asymptotes of its own. So up to 90 here, this is 90 here, that's here, well, minus 90 basically. Then as you keep increasing omega, then the tan, inverse tan comes back here. And then finally, when you reach a very large number, you're back here at 180 again. So the argument plot for the second order looks something like these lines here. Again, depending on the value of the damping factor. Notice that the damping is inside of here as well. So when the damping is 0.7, we have this sort of red line here. So it starts at 0 and it goes all the way down to minus 180. And then when the damping is very close to 0, like 0.01, notice we have a very sharp, it stays, and then it very sharply changes from 0 to minus 180. Yeah? You have the cumulative in your notes, you have the two graphs, one on top of the other. So you could see how as the magnitude changes, you could see that at the same time that the phase changes as well. So they lower the damping, the higher the peak, as the damping gets higher, this peak goes here, and then the phase response, the higher the damping, the sharper the transition from 0 to minus 180. It passes through minus 90. Yeah? Everybody following that? Make sense? Right? Remember what we doing again? For anything, you give them the transfer function, which is some function of S. You take the transfer function and you make it now a function of j omega, right? 3, you take the factors, meaning zeros and poles. 4, you put in the standard form, and then 5, you plot magnitude and phase. If when you getting the poles and zeros, you get complex poles, you need to look at the damping zeta, and then you need to get, from that, you need to get the resonant frequency omega r. You need to calculate the magnitude of the response at that resonant frequency, right? Convert to MR in dB, and then plot. All right? Plot the magnitude and phase. All right? Many times, right? So here's one that you'll try for homework, just after you read through the lecture again and you listen to everything. Try this one, and we will take this up in one of our revision sessions in a while. All right? What I do as an exam type question is that I take two approaches. Sometimes I could give you something looking like this. All right, let me just get back that a little bit here. Hold on. Sometimes I will give you, let me go wrong here. This one, right. Sometimes I can give you a question like this and ask you to do everything here. What is the corner frequency? What is the fall off rate? What is this thing? And then to sketch the magnitude and phase. Or I occasionally give you the other way around. I give you something looking like this. Right? So I will take a response, a particular response, and I will give you something looking like this. And you on the plot, and you have to figure out from this, what is A, what is MR. You will see it in decibels, so you need to figure out, you'll get from MR, this is MR dB, so you'll get the magnitude response. And from that, you need to calculate zeta. And then from that, and of course, from the response, you could read what the resonant frequency is, and then tell me what, fill in the blanks, basically, on the transfer function. Solve for A, solve for zeta, and give me what the answer is. So I have done it both ways. And when I start, I'll put up the past paper, start putting up past paper questions shortly. You will see both approaches. All right. But as I said, your job, you need to remember this particular expression. If you could derive this one here, then it's very easy for you to get this one. But both of them commit to memory, because the question is going to ask you to derive, you're either going to be given this and you have to calculate these two, or you're going to be given these two and you're going to have to calculate this. All right. So one of either way, you need to know the formula. Same thing here. All right. And you'll see where we use this approximation with omega equal to omega naught and omega being approximately the same. All right. So, any questions? Questions, comments? Right? Think about it too, and we could repeat it when we doing our reviews or so on. We still have time, right? So if you have questions, you always feel free to bring it to me. If you think of something after you watch it and you want to ask me some questions, bring it to me in class tomorrow. Or if you think about it and when you're doing the problems, we have questions, well, of course, we'll take it up at that point in time. But based on what we did today, right? Remember what we studied today was what happens with a second order system when there are complex poles involved, right? What we're trying to do, remember the whole purpose of the Bode plot is so that you don't have to physically plot this thing out like that. What you need to, what we want is to approximate the behaviors using straight lines. Okay, to allow us to get a very quick idea of what something is doing. Okay, of course we could get lazy and when you're doing that with more complicated systems, because you have things like MATLAB and scientific other software and so on that might assist you. But again, as I always tell people, MATLAB and other tools of that nature are only as good as what you tell it to do. And if you misinterpret something and you put in the information incorrectly and just simply rely on the answer that it is giving you, right? You could run into problems, which is why it's always good to be able to at least do some sort of pen on paper, quick calculation or quick assessment to know what to expect. And if what you're expecting and what the software, what the real answer is, are not in the same ballpark at all, then you have to go back to your model and you have to go back to how you entered it and what you put down on paper. Okay, always know what is the expected sort of range of answer for any problem, not only here, but in the electronics and in your circuits and that kind of thing as well. All right. So any questions? All right, okay, so if that's the case, that's it for today's class. Let me stop the recording.